No, better, it's positive, right? Smallest that thing can be is 1. X is real here. And so I can take the square root of both sides, and I get lambda minus x is equal to like plus or minus the square root of 1 plus x squared. Because I don't know a priori before the fact whether or not that left-hand side is positive or negative. I got to allow plus or minus the square root. And then finally, this gives me lambda is equal to x plus or minus the square root of 1 plus x squared. But what was lambda? E to the y. So we have worked our way to e to the y is equal to x plus or minus the square root of 1 plus x squared. Which is it, plus or minus? So when you do algebra like this, sometimes you end up adding a solution that wasn't really there. That kind of solution is said to be extraneous, right? I usually tell students that if I was to be a rapper, I would be extraneous G, and then my tag would be, I'm not even in the solution set. No? Wow, it was, yeah, hard audience. All right. You guys like, we're into country. Ah, you're dead to me. Let's see here. No. Minus is a hard pill to swallow because minus is x minus something. Is 1 plus x squared square root larger than x? Think about it. This is larger than x in magnitude, right? You're taking something, squaring it, adding 1 to it, square rooting it. That's larger than that thing again. So this is larger in magnitude than x, which means that if I subtract this is negative, exponential negative, oh no, 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 no. So it's just the plus, that's the solution here. And then y is equal to the natural log of x plus the square root of 1 plus x squared. There you go. Or, what was y? Inverse hyperbolic sine. So there you have it. That is the inverse hyperbolic sine written as a logarithm. Similar formulas. So in other words, I could have written over here, well, come on, obviously it's the natural log of x plus the square root of 1 plus x squared plus a constant. I mean, right? Come on, folks. Obviously, right? I don't think it's at all obvious, but it's true. So similar formulas are known for the other ones. I'll write them down for you. I'm not going to derive the other ones, but for the sake of completeness in here, let me write them down for you. So here's an awful question. Can you see why the equation I just boxed would allow us to find out what the derivative of inverse hyperbolic sine is? There are also formulas for hyperbolic, inverse hyperbolic secant, inverse hyperbolic cosecant, and inverse hyperbolic cotangent. I'll give you the coth. This one's kind of interesting. Check out the domain for hyperbolic, inverse hyperbolic cotangent. So what is, I mean, if you think about, this is kind of an interesting thing, right? The range for hyperbolic tangent is from -1 to 1. What happens if you look at a function which is 1 over that, 1 over that? Like 1 over tanh x, right? This is coth x. What are the outputs there? This, this is between -1. What happens if you look at the values going from like -1 to 0? You're approaching -1 is like the smallest you can get to, but then as you put those really small really small in magnitude but negative numbers, you're approaching infinity, minus infinity, for the negative values. And then on the flip side, as you plug in the values for tanh, which are going from 0 to 1, but you're going arbitrarily small, right? So you're dividing, which means that they're getting really big. The weird thing is the range of coth is the complement to the range of the tanh. It's like 1 to infinity and -1 to minus infinity. So I think you could say that this is equal to coth inverse of x plus a constant for epsilon of x greater than 1. So like you put these two together for different cases. Anyway, I don't really much talk about hyperbolic. For us, we will mostly focus on inverse hyperbolic, sine, cosine, and tangent. That's enough for you guys, okay? Like if we run into the need for the other three of them, the inverse hyperbolic secant, cosecant, and cotangent, well, we'll deal with it when we come to it, but I don't think I need to talk more about it here. So, after all of this, you might ask a question, right? And I think the question that would be good to ask is, why on earth are these called hyperbolic? Sine and cosine, right? Do you see a hyperbola anywhere? The cosh? Ah, well, yeah, it's kind of fair. Yeah, okay, I can. That's imagination. I like that. But yes, sort of. So let me explain to you a little bit about why these are called hyperbolic sine and cosine. I don't know if you knew this or not, but sometimes sine and cosine are called circular functions. Do you know why that is? I mean, there's various reasons, right? Sine and cosine are connected to the unit circle, and if I have the unit circle, then the coordinates to the unit circle are what? Sine and cosine, right? Cosine's the x, y is the sine, right? If we look at the unit circle, maybe you've been taught to learn standard values for sine and cosine using that circle picture, remember it? But we can talk about what's called a parameterization of a curve. And I'll just give you two examples. These are like probably the most important examples. So we'll start here. X squared plus y squared equals to, let's say 1. I'll keep it really simple. This is the unit circle. A parameterization of the unit circle is giving a formula for x and a formula for y in terms of another variable here, t. So t is called the parameter. So to parameterize a curve, we give two equations, one for x and one for y. So sine and cosine parameterize the circle. Why is that? In order for it to parameterize a given curve, right, so the curve, I'm giving you the circle. This defines the circle, right? Defines the unit circle. How can I see that I have a parameterization of the unit circle? Very simple. I take the parametric formulas and I plug them in to the definition. If it works, that's a parameterization. Do sine and cosine work? What happens if I take x equals to cosine and y equals to sine? I get cosine squared plus sine squared equals to 1. So sine and cosine parameterize a circle. All right? Example 2, you could talk about a hyperbola. This defines hyperbola. What that looks like, let's see here. If we put y equals to 0, x is going to be, x squared is 1, so we get plus or minus 1. So this hyperbola actually opens sideways like that, all right? These are the asymptotes. They're not actually part of the hyperbola, right? All right, hyperbola. Suppose I wanted to parameterize the hyperbola. Guess what? If I write down x equals to cos t, and if I write down y equals to sinh t, all right, you can check. And here, what should the t range over? I mean, you can choose whatever you want. I'll choose the whole real line. Do those parameterize the hyperbola? Plug them in, right? Cos squared minus sinh squared is 1. So these parameterize the hyperbola. Yes, sir?
What is the graph? I thought it was like a circle.
This is the unit circle. Yeah, I didn't even, sorry, I didn't graph the unit circle. My bad. Yep.
For the example 1, why are you making the range of t 0 to pi?
Ah, well, my choice.
Oh, you choose it.
Yes, there are many choices. We'll talk more about that. So note, cos squared minus sinh squared is 1. And this is x squared minus y squared is equal to 1. In other words, it works. So this is a parameterization of a hyperbola. But actually, not the whole hyperbola, because what do we know about cos? It's larger than or equal to 1. So to be more precise, this is simply a parameterization of the right branch of the hyperbola. And more than that, I can tell you, because sinh is always increasing, y is always increasing with t, it has this direction. Over here, this was a parameterization of the circle. This actually gives me a counterclockwise parameterization. So parameterizations also give an orientation to the curve. Anyway, it will take me at least an hour to describe what I mean by parameterizing a curve, but that's the next thing we're going to do. We're going to look at how to parameterize curves. And as you can see, cos and sinh, important page in that story. So. Thanks, guys. If you haven't top-hatted already. Oh no, I said the word. Try not to say that word. I'll try to not speak it out loud. It's too late.